I cannot give you that answer. I don't know. Yeah. It's a good question to think about. See, I'm also learning about it. I cannot give you that. Yes, everybody is learning. Other questions? It's a good question to think about. Okay, so what I've done now, the previous lectures were all taken from, let's say, the revised edition of the Essential NMR. This is what where you have the PDF files of the internet. What I've done now, I sent to Professor Balwinder also this file. I don't know if you had a chance to send it out. So you will receive it by email. And that actually covers the material for 2 lectures, and it's sort of extracted or composed from Essential NMR and some others. In particular, the needs for the chemist when they want to do NMR. So the physics part will follow afterwards. So matrix, we'll do imaging, we will do relaxation measurements, which is a lot of hardcore physics there. And so this is something I put together with the help of Karva Pal Singh, and I mentioned in my very first lecture, he is a student of this university, he does his PhD with me, and he is a very good chemist, and I'm not a good chemist, I'm a physicist, so I have real problems doing chemistry, and so I need the help of smart people like Karva Pal that do the chemistry for me and explain to me all the intricacies involved in reading and analyzing chemical spectrum. So let me pick up again on the Fourier transformation. We go through the practical aspects, and in fact, Professor Balwinder will then give you a demonstration for those interested, probably this afternoon, and show you some of the tricks, what really happens when you measure an NMR spectrum. So one thing is you have to do the Fourier transformation. You have to go from, where's my laser pointer? Here. This is the signal you acquire, and then you do the Fourier transformation. And the Fourier transform of this signal is your NMR spectrum that you see. So that's the basic step that always needs to be done, is the Fourier transformation. And the next step that needs to be done when you do an NMR spectrum, measure an NMR spectrum, is the phase correction. Because the signal, probably I should go to the blackboard, the spectrum, we call it S of capital omega. Omega is the frequency in the rotating coordinate frame, or the frequency offset relative to tetramethylsilane as a reference compound put in there, because it has a very high shielding, gives you only one resonance frequency. And typically that's set to frequency 0. That is represented as a complex number, because the Fourier transform itself can be written as integral S of t e to the plus or minus omega t. No, this should be capital omega t. So even if this is a real function, like the function presented over there, you multiply with a complex function, so the result of that transformation must be a complex function. And just write the real part and the imaginary part without ever calculating this. So I just tell you this is a complex number. Now you want this number actually ideally to be something like an absorption function plus I times a dispersion signal. And the absorption and dispersion signals, they are shown here. That's the absorption signal, A of omega, that's the dispersion signal. But you don't get it. What you get actually as a result is e to the I phi. So you get this complex function multiplied with a phase factor. This is just a complex multiplication of what you want to have times this e to the I phi. And that phase comes in, that phase error comes in because the signal takes time to migrate from the receiver coil through all the different electronic components until it ends up in your computer. It's one phase error. Travel time for the signal electronics. The other is the dead time. You don't see the beginning of the signal. You don't see it beginning at the maximum because the spectrometer is blind. It cannot detect so fast. Actually, you would have to start detecting in the middle of the radio frequency pulse. And that's just, paying attention while you get a big bang over your head. You can't do that. You need to recover afterwards. And so the recovery time is a dead time, so you start seeing it here instead of seeing it in the maximum. And this whole thing can be recovered by then saying, okay, look at, instead of S of omega times e to the I minus I phi. And that is A of omega plus I d of omega. And then you have, if you multiply your measured spectrum or your calculated spectrum with that phase correction factor, you have the absorptive and the dispersive term. And usually what people show when you see an NMR spectrum in some publication is only the absorption term. And there's actually a relationship, a mathematical, with the imaginary term, but that is not good in terms of resolution. In other quantities, you don't look at that. And it is always good to look at that phase-corrected spectrum because it has narrow lines. There's a way to always plot, to also plot the magnitudes, S of omega magnitude, and this would be A square plus I plus D square and the square root. That you could also do, but that's cheating and you get broader lines, your resolution suffers. People in imaging do that very often. They calculate the magnitude square to get an NMR image to save the phase correction term. Now I lost the cap. Okay, this will dry out if we don't have a cap. This is a phase correction step, and you will probably see that how it's being done, so you know how to get a nice spectrum then. That's the next term. And then there's another trick which I have not addressed so far, and that is the trick of what we call zero filling and apodization. These are two steps in the data processing. And zero filling means that this is your recorded signal, and typically you want to record it all the way to the end. To the end means until your signal disappears in the noise. But that means that doesn't mean that there's no signal anymore, just you can't see it because there's noise that you receive in your receiver even when there is no signal. But the resolution in terms of the digital resolution, and that now gets probably a little bit complicated because I at least realize that my students don't know how a signal is stored in a computer, a continuous function. Do you know that it is stored as a set of numbers in the computer? Yeah, these numbers, but for each, and that is done at discrete times, so you don't have a continuous flow, but the numbers come at little increments of time delta t. And that the time increments at which they are recorded, they give you a total bandwidth, the spectral width of the width of your spectrum, and the total length which you put into the Fourier transformation tells you how the data points, how they are spaced in your spectrum. So you want to have a very narrow set of data points that you see even a narrow line somewhere in your spectrum. But to see that, to get a high digital resolution of your spectrum, to have these data points that tell you the amplitude in your spectrum at each frequency interval, to get that, a fine spacing there, you want to have a long recording of your data. But you don't have that long recording because your signal goes to zero. But you can artificially extend it, typically by a factor of at least 4 or 8 times its original data set. That is called zero filling. It's a standard way of artificially enhancing your resolution in the spectrum. And then suddenly, lines that appear not to be split, you see a better splitting in the lines. It's a very nice trick. It's a routine operation on spectrometers. I don't know if you have a chance to show it. It's sort of one of the things one can do. And the other thing that is people often do is resolution enhancement. And resolution enhancement means, suppose you measure the light green here, or yellow, is the same signal as here, but you want it actually to not decay so fast, because the faster it decays, the broader is the line. You want to decay it slower. You can artificially make it decay slower by multiplying it with a positive exponential function so that you decay, or with an exponential, with a Yeah, so multiply it with a positive exponential function so that your decay now follows the red envelope. So you just blow it up. Of course, anything that's noise here will also be magnified. So you introduce artificial noise, but you effectively narrow your line. And I hope that this is a bad thing here. But you can see that the original spectrum, being the blue line, the broader one, is what you get from Fourier transforming the original signal, that signal. And when you Fourier transform it with resolution enhancement, you get the red spectrum underneath, which has much narrower lines. So there's a trick to enhance the resolution to get, two tricks. It's a digital resolution by zero filling, and the resolution from the recorded signal in the spectrum by apodization, by resolution enhancement, by magnifying the tail. And you can also do the opposite. You can suppress noise by multiplying with a function, with a blue function, then your signal only is underneath the blue curve. And that means all the noise that's in here, in that tail, gets also suppressed, and your signal to noise gets better, but you suffer from spectroscopic resolution. You will not see the details anymore. So these are tricks a little bit advanced, which one plays at the spectrometer. And sometimes when you buy a new spectrometer and you have several manufacturers that compete, we used to do that when we still had several manufacturers for high resolution spectrometers, like Bruker and Varian. They would play these tricks on you, and then you would have to ask exactly, put your sample there, measure the spectrum, and then show me while you process the data, so that you're not being tricked. So these are games one can play, and they're actually quite helpful when you have a complicated case to analyze. Your signal to noise is not good enough, or it is so good that you can actually enhance the resolution. You can play these games. Okay, so we discussed magnetic shielding. This is just a reminder from what we have done before. It's the the motion of the electrons in the neighborhood of the nuclei that introduces, basically corresponds to a current. The current shields or de-shields the applied magnetic field and shifts the actual resonance frequency. So depending on the shielding or de-shielding of the nucleus, you will see different chemical shifts, different resonance frequencies for one nucleus with one particular gyromagnetic ratio. Like the hydrogen atom, and you have a range of 12 ppm. Professor Ketterpal mentioned 20. That's very rarely seen, but 12 ppm is good. Is a good number. And carbon-13 is 250 ppm. But carbon-13 also has a lower resonance frequency, so your total gain in resolution is something like a factor of 5 against protons, but that's still very significant. We also, I want to remind you again that the chemical shift essentially, first of all, is a fingerprint of the chemical structure. So you have many lines, discrete, narrow lines, and the discrete narrow lines allow you then, once you know where they come from and you're able to read them, to assign chemical structures like the side chain in polyethylene over here from that spectrum. That's a carbon-13 spectrum. We drew the analogy to a spectrum of radio frequency of the FM radio stations in a particular region, where depending on where you are, you get a different set of lines. They are also discrete lines, and that is a fingerprint of geographic position. So now, what do we work with? There are chemical shift tables, and I did not know that they were introduced at the time of Paul Lauterbur, which is something I learned in Ketterpal's lecture in the one before this morning. Paul Lauterbur is actually the one who got the Nobel Prize for discovering magnetic resonance imaging. So he also measured the first carbon-13 spectrum, which I didn't know. And his colleague at the time then also immediately set up and said they tabulate, record, measure many, many compounds, chemical compounds, look at the chemical shifts, and figure out what are the chemical shifts for particular chemical groups. In those days, they used a different scale. They didn't use the chemical shift scale. That was introduced later. But this is now translated to the chemical shift scale. This is not carbon-13. This is protons. And you can see where the different chemical shifts are for particular chemical groups. So when you have your Nmr spectrum and it has properly been recorded that you have the chemical shift axis underneath, you can go and you immediately see where the different resonances are. And somewhere the CH3 groups, where are they? They should be all the way to the right. I don't see a single one. I should have looked at that before. CH.
So because they're on the bus side, saturated in games.
Oh, here they are. Yes, thank you. Thank you for pointing them. You do it all, right? So they're over here. So the methyl groups are always here, right? And the methylene groups are somewhere here. Double bonds are in this region. Aromatic groups are around 7 ppm. And there are some exotic cases where you have lots of, let's say, removed electron density from the position of the nuclei. Then you are at the very high ppm range. So this is, so in a way you can say that nuclei that are highly shielded, with lots of electron density at the site of the nuclei, they appear on the right of the spectrum. And the other nuclei where the electron density has been removed, which are de-shielded, they appear at the left of the Nmr spectrum. And oddly, the ppm scale goes from right to left. So typically, at least in my part of Europe, they draw the scale from left to right, but they also draw it on the other side of the string. And they really think are more likely to think this way. So this is a typical, a map that will help. Today, I mean, there are also books that allow you to calculate chemical shifts from chemical shift increments for particular chemical groups with correction factors. That was a technology when I was a student, and today you have software, computer programs that tell you. You type in you propose a particular chemical structure, and they will tell you the chemical shifts for this structure, and then you can compare. Or you put your spectrum in and you get a proposal for the chemical structure. So the techniques have advanced quite a bit, but it's not in such a way, as much as I understand, that it's completely reliable and you can say, well, that the computer told me it's that molecule, so I continue with that one. It still needs your critical judgment as a scientist. There are, what is next? Yes, there are carbon-13 chemical shifts. I mean, this is now we go back to Lauterbur. Again, you have the different chemical groups that produce signals in different ranges. You see now the range doesn't go from 1 to 20. It goes from 0 to 200. Actually, it could go to 250 in exotic cases. Again, aromatics, sort of the general scheme is roughly maintained, that the highly shielded carbons are on the right, and the de-shielded ones, the ones with lower electron density in the vicinity, they are at higher ppm ranges. And those are helpful to have a very first impression of chemical shifts. Now, that we had before, and this picture on the coupling, and I was asked to actually go through that again because it seems to be a little bit difficult to figure out the way how that splitting works. And so if we take the ethanol spectrum, and let me plot that again for you, the ethanol spectrum, then it is basically the OH group. Then we have the CH2 group, which gives us a quartet, and then we get the methyl group, and that is the OH, that is the CH2, that's CH3. So that's the spectrum which is seen right here. Okay, the bottom line, that's the spectrum. That's a regular spectrum that you can observe. And the question was, how does that splitting come about? And let me repeat that we have the CH2. There are two hydrogens in there. C is in this case C12 because there's only 1% carbon-13. So we discuss the C12 H2 group. So there are two spins in here. The two spins can have these four different relative orientations, both up, up, down, down, up, and down, down. And these orientations, these spins orientations produce magnetic fields. And these magnetic fields are communicated, distort the orbitals of the chemical bond to the CH3 group. So and that distortion of the binding electron, of the orbitals from the binding electrons, is sensed by the spins of the methyl group. So in the end, the methyl groups experience different magnetic fields at the site where they are, the methyl protons, depending on the orientation of the methylene protons. If they're up, down, 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 down. So that means the methyl resonance splits into the 4 lines with amplitudes 1, 2, 1, which you see here, 1, 2, and 1. And the methylene does the opposite. It sees the 8 orientations possible by the 3 hydrogen atoms of the methyl group, which means the methylene will split into 4 lines with total relative intensities 1, 3, 3, 1. 1, 3, 3, 1. Did I plot that right? I hope so. Okay, so here is a summary for CH3, the methyl group. That's not a good L. Should make it a better L here. So the methyl group is a total spin of 3 spins 1/2, a total spins of 3 halves, gives us 2i plus 1 lines, n equals 4, so it gives us 4 lines, and the ratio is 1, 3, 3, 1. And for the methylene, total spin 1, 2 I plus 1 is 3. It gives us a triplet with amplitudes 1, 2, 1. That's what we observe. And the other ones, when we magnify, is then the coupling, and we see the carbon-13 CH group here, the carbon-13 the carbon-13 CH2 group giving rise to, where are they? So we have to see a triplet, and a triplet, that would be this one here. This is a triplet, and that probably is 1, 2, and then we see the quartet, and then we see the triplet being split into a doublet of triplets for the CH3 group. So that's then the carbon-13. These are the carbon-13 satellites. Okay. Here's a more complicated case, just to exercise that part. That's isopropanol. We look at the resonance of the CH group. Okay? And the CH group has 2 CH3 groups at magnetically equivalent positions. So we have a total spin of 3 halves here, and a total spin of 3 halves here. And so it means 3 halves plus 3 halves is 6. And then 6 halves, 2 times 3 plus 1 is 7. So we have 7 lines that we expect, and we observe indeed 7 lines. 1, 2, 3, 4, 5, 6, 7 lines over here. That's the methyl. It's only 1 hydrogen, so it's low intensity, and then it splits into 7 lines. And when we want to figure out the amplitude, the relative amplitudes, we have to look at all the different combinations, and they're shown in here, the different combinations. There are plenty for the 6 spins that we have, and we see that we have the ratio of 1, 2, 3, etc. For the signal amplitudes that you can see. So that's a combinatorial analysis of the splitting and of the line amplitudes, which you see. But you also see already that the CH3 groups, the methyl groups, are low ppm values. So here we are, that's ppm equals 0 ppm, where tetramethylsilane is by definition. And then you see the CH group over here at higher ppm values, which is far more de-shielded than with the splitting accordingly. The OH group appears depending on the pH, so that is, can vary from, it depends very strongly on the solvent where that appears. Okay, now indirect couplings. Chemical shift it bears a chemical signature. So chemistry is based, the chemical analysis, on the chemical shift. But also the coupling, the indirect coupling, the J coupling, which we discussed before with a very complicated approach to it with our tensors. Also, the J couplings are characteristics of the chemical structure. So also the J couplings bear chemical information. So the chemical analysis focuses not only on the value of the chemical shift and the multiplet splitting in terms of how many lines and what amplitudes, but also in terms of the width of the splitting, of the separation of lines in the multiplets, which gives you the J coupling. And this is shown here, that you have, depending on the structure of the molecules, different J couplings. They range between small numbers, 0 to 2 hertz, and all the way for the trans coupling over here to 18 hertz, so they can be rather large. These are homonuclear couplings between protons and between two protons. You can have couplings between protons and carbons, and they give rise then to the carbon-13 satellite. When you have proton carbon-13, right, and that is 125 to 130 hertz, or other values. It's too bad there's not a picture that it has CH2 groups and CH3 groups, because these couplings, heteronuclear couplings, proton carbons for CH, CH2, CH3 differ significantly enough to exploit them, so that one can then design NMR experiments that allow us to look at the carbons that are only bound to CH, CH2, and CH3. It's a very famous DEPT experiment. For those who have heard it, I'll show you spectra for that. But we see there's a variation also in the heteronuclear couplings that one observes. And similarly, there are couplings in phosphorus NMR. There are heteronuclear phosphorus-carbon couplings. And here's another phosphorus-carbon coupling, which can go through multiple bonds. The more bonds between the coupling partners are, because the coupling goes through the chemical bonds, the smaller will be the J coupling. So the distant distant coupling partners have smaller J couplings. And there's also a sign alternation that goes along with the number of chemical bonds between the coupling partners. Yeah, that is also something interesting. It's the Karplus curves for 3 J couplings. So we have the two protons here couple, A and B. Then we have 1, 2, 3 chemical bonds. And depending on the dihedral angle, in this case it's 180 degrees. Over here it is 60 degrees, and also over here it is 60 degrees. One observes different J couplings. So from the value of the J coupling, if it's a 3-bond coupling, you can learn about the dihedral angle and thus about the configuration and conformation of the molecule that you're analyzing. So it's a rather strong dependence of the J coupling. This is also helpful in deriving chemical information from the J coupling. And I should probably mention one interesting thing. I mentioned that the chemical analysis requires homogeneous magnetic fields. The J coupling can be measured in inhomogeneous magnetic fields. And people recently published, just 2 years ago or last year even, experiments that people can measure J couplings of crude oil with these well logging tools by doing a double resonant proton carbon experiment to measure heteronuclear J couplings, to get information about the value of the J couplings, so that they learn something about what type of oil is underground by a chemical analysis, which is rather interesting. And this is something that probably will be exploited more in the future, to study J couplings with simple NMR tools to derive chemical information. Okay, so here's another NMR spectrum, and we can analyze again. What is it? Acetyl acetate, very simple chemical structure. We have a methyl group there, we have a methylene, and we expect the methyl group to be at low chemical shift values and the methylene group at higher chemical shift ranges, depending, we can look at our chemical table, or the table with the chemical shifts, and we will see that that assignment is meaningful. Now, depending on the solvent, the OH group can shift across the spectrum, but similar to the ethanol spectrum, when we now magnify that spectrum by a factor of 100, because there's 1% carbon-13 in there, and the rest is carbon-12. This is the carbon-12 proton spectrum with of the protons attached to carbon-12. We see the satellites of the protons attached to carbon-13. And they're always there, and there are actually tests of taking the line widths at the height of the satellites in the carbon-13 spectrum to judge the homogeneity of the magnet and the quality of your shimming and the quality of the spectrometer, depending on the satellite analysis. On the other hand, if you do measurements of, let's say, compounds, we have large concentration variations in concentrations. Let's say lots of water or lots of solvent, that gives you a peak, and you want to see a small concentration of solute, then it is hard to figure out what is carbon-13 satellites and what are peaks of your solute. So one has to be careful there, and one has to be aware of the existence of these carbon satellites. Okay, so here we have a slightly more complicated spectrum. Now we have a whole range of different groups. There's a CH3 group here, there's one there, the CH2 group and CH groups. So as a general rule of thumb, we expect now that the chemical group, the CH3 groups, are more de-shielded, so that it should appear on the right. And right now you wouldn't know if this CH3 group or this is more shielded. So at least as a physicist, I would have problems to say that. And but you would know that the CH2 groups you would expect over here, and the CH groups you would expect at higher chemical shifts. But again, it would be hard to say if group 7 or group 6 is at higher and lower values. Now what you can do to figure out is that you look at the splitting patterns of the J coupling patterns, and you take those as a help to figure out which chemical group is which one in the spectrum. So methyl group is next to a methylene group, while this methyl group is next to a CH group. So here I have only one proton that couples, so that would give us a doublet. And this one is 2 protons, and the CH3 group would actually split into a triplet. So in fact the triplet is seen over here, so that must be the CH, this line, because it's a triplet, must be the CH group 1, which in fact it is, because I've given you the solution already of the analysis. Well, that one first of all is a doublet, which is then further split by the presence of that CH, so it's a doublet of doublets, and that's why we see that very narrow splitting from the 3-bond J coupling to the proton number 6, to the CH group number 6. So that explains these two. This was clear, and here of course it gets very complicated, but we can say that the CH group number 6 will have a strong coupling with the CH group number 7, so we expect that to be a doublet, because the proton 7 can be up and down, so the transition here will be split into a doublet. And then there will be a small coupling to the CH3 group. So that means we have a doublet, which suggests is this one, and a small coupling, which means a further splitting of each peak into a quartet from the CH3 group, which gives rise to these 2 peaks. And this is a mess, of course, because now we're looking at number 7, that's the only one left, and that is split by the J coupling to the CH3 group and the J coupling to the CH group. So it's a doublet of quartets, but now the quartet, the splitting of the quartet is much higher, because the coupling of that CH to the CH3 group is much bigger. Okay, so this is what the chemist goes through for the physicists among us, right? And so it's their analysis and their world, and it gets more complicated, and I don't know how many examples I have. Oh yeah, I have one example here. Again, color-coded, relatively simple molecule, where you can see the hierarchy of the chemical shieldings, highly shielded. This actually is most de-shielded, and this is less de-shielded, and that gives rise to that sequence of peaks. And you again can say, here it's very hard to see a splitting of the CH2 group, because the next one is 3 bonds away, 1, 2, 3 bonds for the protons, and that again is 1, 2, 3, even 4 bonds away, the coupling. So this is probably one line which identifies that CH2 group as this peak over here, and the CH3 group over here, oops, there we are, also doesn't couple to anybody else, except maybe a weak coupling to the CH2 group, but it has to be at low ppm value, so that's that CH3 group, while this one here shows couplings, so CH3 group, so that is split, and it must be this one, and that couples to this one, so the CH2 group here must be that one. So this is a relatively straightforward analysis you can do by inspection of one-dimensional spectrum. But it's not always that easy. And because it's not so easy, then one has to go to multidimensional spectra. And that's another lecture when we do multidimensional NMR spectroscopy. But I have a few slides left. And I want to mention, Professor Ketrapal mentioned shift reagents. And shift reagents have been used in the olden days when people had low-field NMR spectrometers. When the, let's say, maximum spectrometer frequency was 100 megahertz. Today you have 100 gigahertz if you have a lot of money. So what's your highest field you have here? 400? 500 even. Perfect. Wonderful. So you don't need the shift reagents. Or maybe you use shift reagents. But if you buy one of these tabletop spectrometers and you have only 40 or 60 or maybe 80 megahertz, you may want to use shift reagents. And they do the following. You have these chelates that actually have paramagnetic centers, europium in there. And the europium then basically exerts a magnetic field at, from its complexion site with the target molecule, and this way adds an additional local magnetic field which shifts the NMR frequencies of the target molecule. And you can see here now, oh, this is the fluorine, now here's the proton chemical shift. Now suddenly the proton chemical shift rate range extends, it doesn't even say what molecule that is. Oh yeah, no. Yes, it is this molecule over here. That's the europium from the shift reagent. And that's the chemistry of the shift reagent. So you can see that now the proton chemical shifts, they go all the way to 30 ppm. And this is beyond the regular range, which goes to 12 or at most 20 ppm. And Ketrapal has actually measured a number of spectra for me with different concentrations of the shift reagent. And he measured adamantanol, and he used 0 shift reagent, then all your lines appear in that chemical shift range between 0 and 8 ppm. And if he uses a ratio of 1:1, then your shift is spread. As your concentration increases, the chemical shift moves over. So that line then from 2 or 3 ppm moves all the way to 12 ppm. So that's something that stretches your chemical shift range and helps you to increase the chemical resolution without going to more complicated experiments, but you will have to go to more complicated to use some chemistry. So the final thing, I think I need to close at 1, right? So the final thing is what I want to mention is the effect of strong coupling and the effect of field strength on the multiplet splitting and multiplet line intensities. And there's something that's called the roof effect. So what one measures at high magnetic field, when you have a lot of money, this is we are only 100 megahertz more than you in Aachen, so that's all we have. And so this is a 700 megahertz magnet. And if you measure an NMR spectrum there of, let's say, of 2 spins, coupling by J coupling, then you see spin A and spin X, and the J coupling is the splitting between the 2 lines, and all 4 lines have the same intensity. This happens when the frequency separation between this chemical shift and this chemical shift divided by the splitting, by the value of the J coupling, when that is large. Now when that approaches 1, then something happens that first of all the two doublets, they move closer together, and that means now that this is drawn on a different scale, that then the J coupling, so that splitting really corresponds to this splitting over here. I should change that in the text.
So it seems to be quadratic.
Pardon?
This one seems to be quadratic.
It's not a quartet. This is done at lower shift, and you have the J coupling here, and you have the J coupling there. And now you have the strong coupling limit. And the strong coupling limit you observe at lower fields. And that means your lines appear to be a quartet, but they're not. For the quartet, you also would need the same separation there. So you have one chemical shift here, you have that doublet, which was this doublet, different magnification. That's my mistake. I should change it. And so a different stretch of the chemical shifts there. And the other line splitting is over here, and if they move even closer together, then these lines go even smaller and they get even higher. And you get distortion, and you may mistakenly then say, oh, it looks like a quartet, my analysis is done. If one doesn't take care of the fact that you have a roof effect. So that's a little danger when you do analysis with low field instruments. You have strong coupling, that's a strong coupling limit, and that is harder to analyze. And also the multidimensional NMR experiments that we will learn later, like the 2DJ spectroscopy, show all kinds of strange additional lines, combination lines, which people were familiar with in the 1960s, but our generation doesn't really work with them.
But how it actually comes into picture?
Fun?
Right.
How that comes into, oh, you have to work through the quantum mechanics. And then you understand it. And it's actually the AB or two spin system is something that can easily be solved. It can be solved, okay? And then you work out the signal amplitudes and the line positions and the splittings, and that drops out nicely. We did that, students, we did that as an exercise. But as students, we still had low field instruments, so we really had to worry about the roof effect. And now one has to worry about it again if you have low field instruments which you set up in your lab to do reaction monitoring and other stuff. So I think the computer doesn't even move anymore, so it tells me, yeah. There's the last thing I want to mention, and probably I will stop right here then, is something that is magnetic and chemical equivalence. That is something really complicated. You may have molecules that react the same way, and then they are related, you say they're chemically equivalent, and they're related by symmetry, and there's a symmetry operations that produce, by rotation and mirror symmetry, etc., that give you the chemical equivalence, but that doesn't mean that your peaks in the NMR spectrum of the protons involved arise at the same frequency. For them to arise at the same frequency, they need to be magnetically equivalent. And magnetically equivalent is illustrated here with two molecules, one being magnetically equivalent. The definition is the J coupling of one molecule to all the other must be the same to all the other molecules that bear a spin. So the J coupling of A to X to here is the same. Of A and X, and this one to here is the same. Well, here you have a J coupling that's different from A to this X and A to this X. So they are magnetically not equivalent, although A and X are chemically equivalent hydrogens. So the difference of magnetic and chemical equivalent is a little bit advanced for the physicists among us, but it's something important and useful in the analysis of proton spectra. So we will stop here, and I thank you for your attention, and if you have questions, please ask them. Too much chemistry? Okay.
So before we discuss further, there are few announcements that I would like to make. One is, I know it is very cold in the morning, but it is requested to be kindly on time, because we have